In this video, I'm going to use the variational method to calculate the energy, the ground state energy for a helium atom. And so this is a little bit more complicated because the helium atom, well, first it has two protons in the nucleus, but it also has two electrons which are interacting with each other. And so you get this sort of three-way interaction between everything, and so that will complicate things. But just as kind of just driving this point home, because this is kind of the take-home message, we're using our four-part method here. So first, we guess the trial function with our adjustable parameters. Then we find the expression and calculate the energy. So we'll calculate the energy, the expectation value in the numerator, and then the inner product in the denominator. Third, we will adjust the adjustable parameters by taking the partial derivative of our energy with respect to each of the adjustable parameters. Then fourth, we substitute those adjustable parameters back into our energy expression, and then we can calculate our energy. All right, and so, well, again, this is that flow chart, which is essentially just saying the same thing I went through above, and I've gone through it in the previous couple videos. So, as usual, the lecture notes are linked to in the description down below, so you can look at these a little bit longer if you want to on your own. All right, so we're looking at the helium atom, and we're going to be using the Gaussian test function. But the first thing to notice, as I said, so we have three particles here. So I have this right here, which is our +2 E, where E is just the charge, and that's the nucleus. Then we have these two electrons that are also interacting with each other. So this R1 is the distance from one electron to the nucleus. R2 is the distance of the other electron to the nucleus. And then we have this R1 minus R2 right here, which is the distance between the two electrons. And so we end up with this Hamiltonian right here. So we have these two del operators here, which are for the two different electrons. Then we have this potential here, which reflects this three-way interaction right here. And so we can set up our, well, this is difficult to calculate because of these electron-electron interactions. So it's this term up here that's really causing us a lot of trouble. And this is something that I did in a previous video when I was just looking at solutions to the Schrodinger equation for multi-particle systems. And so we can get sort of an approximation for this by ignoring this electron-electron interaction term. And so what we end up getting is this right here, what I have in this purple color. But this gives us 8 times the hydrogen ground state energy, which is minus 13.6. So that's about minus 109 electron volts, which is 28% off the experimental value of minus 79 electron volts, which is not really that good. But we can use this function here that's, again, it's still ignoring those electron-electron interactions, but we can use it as a test function in the variational principle. And so we have this right here, where we have our 8 times the ground state energy of the hydrogen atom plus this V, which is sort of the thing we want to find here. And so we find the energy of this V term here. So we have to take this integral here, and there is like maybe 2 full pages of math in the Griffiths and Schrader 3rd edition, which I actually have pictures of down here if you wanted to go through all the math that I'm kind of skipping over in this video, but what we end up with when we take this integral is this right here, so 34 electron volts. And so we end up with our minus 109 electron volts plus 34 equals minus 75. And so this is only 5% off from the real value of minus 79 electron volts. So we're getting quite close here. But we can actually do better. And so it's possible to do better since our function ignored the electron-electron interactions. So we can actually, instead of this 8 here and this 2 here, we can put these z adjustable parameters here. So that's our variational parameter. And what this is essentially going to do is give us the shielding of the nuclear charge by each electron caused by the other electron. And so if we look back up here at our system, so these are obviously not static in space. They're constant, well, moving is even a little bit kind of a strange way to think about these electron clouds, but each electron is sort of shielding the nuclear charge from each other. And so when we put this term in here, what we're essentially going to find is that the potential given by the nucleus here is going to be somewhat weakened because there is this electron-electron repulsion going on. So that's going to reduce the charge felt by each electron. It's going to the charge of the nucleus felt by each electron is what I'm trying to say. So after some more math, and once again, these are in the pictures down here if you wanted to look at these in a bit more detail. But what we end up getting is this right here. So this is our energy equal to this minus 2z squared plus 27 over 4z, all that times our hydrogen ground state energy. So then we'll try to minimize by adjusting z. So we'll take the partial derivative of our energy with respect to z, and that gives us this right here. We set that equal to 0. Then we get this in terms of z. And so that's 27 over 16, which is about equal to 1.69 here. And so again, this is telling us the effective charge felt by each electron. So this Z effective is 1.69. So there are 2 protons in the helium nucleus, but the shielding reduces the charge felt by each electron from 2 to 1.69. And so we substitute this back in, so we end up getting this here times our minus 13.6. So when we calculate all that, we get about 5.695. And so that ends up getting us a minus 77.5 electron volts, which that takes us down to 2% off from the real value. So remember, when we ignored the electron-electron interactions, we got down to 5% off from our experimental value. Now doing this, we get down to 2% off from this experimental value, and we could get even closer and closer if we used more complicated test functions with even more adjustable parameters. But this is sort of where I'm going to stop here. So like I said, if you want to look at the math that I kind of skipped over, you can look through the 4 pages that I've put into the lecture notes here from the Griffiths textbook. But still, again, the kind of take-home message is this 4-part method that I've been applying every time, where we first find our test function, which has these adjustable parameters. Then we calculate the energy. We vary the energy with respect to the adjustable parameters. To find what the adjustable parameter values are, we put that back into our energy calculation here, and that gives us the energy that we are interested in, and we want to try to keep getting that as close as we can to the experimental value, because that will give us it'll give us the formula essentially, or the equation for that energy, and that's sort of what we're looking for here. But anyway, that is using the variational method for a multi-particle system, in particular the helium atom. The next video, I'm going to look at what's called the linear variational method, which is it's a little bit different, the steps that we take, and I'll actually show a side-by-side comparison of the steps we use here compared to the steps we use in the variational or the linear variational method in the next video. But anyway, I hope you found this video helpful, and I will see you in the next one.